Good morning, or good afternoon, or good evening. Thank you for joining us for the 24th episode in the Gleeble webinar series. Wherever you are in the world, we're glad that you can spend some time with us. My name is Dan Quigley with VSI, and on behalf of our whole team at VSI, we hope that you and your families, your colleagues, and your communities are staying healthy and safe. As always, our goal will be to keep this webinar to 1 hour or less. If you have questions during the presentation, please submit them using the chat feature here in the webinar. We have some team members here that will be available to answer some of those questions directly via the chat, and if time allows, we will have Q&A following the presentation. Video of this presentation will be available online soon, and certificates will be emailed if you're listening to this live. You'll be able to find a link to this video as well as videos of past webinars by going to our website at gleeble.com and click on the resources link in the top navigation bar, and then click on webinars. There you can view past webinars and sign up for future webinars. Next week's session will focus on digital image correlation tools, which can be used on Gleeble equipment and offer quite a bit of potential for improved non-contact measurement, and in particular with strain measurement across the specimen. If you work in the steel industry, or if you study steel, or if you use steel in an industrial process, then you're in for a treat today, because today's presenter is Dr. Evgueni Poliak, who is a leader in the field and has many years of experience. Dr. Poliak is a scientist with the Global Research and Development Team at ArcelorMittal East Chicago. The title of his presentation is Using Gleeble Simulations to Support Industrial Steel Manufacturing Processes. So this may sound like a simple title, however, the presentation will cover practical applications and various simulations performed at an industrial R&D center, and importantly, illustrate how those results of those simulations can be utilized to assist steel production. And I've had the pleasure of getting to know Dr. Poliak and also had the good fortune of being able to hear and see several of his presentations over the years. They're always interesting, filled with real-world practical information, so I'm sure you'll find the next 60 minutes to be quite valuable. So please join me in welcoming Dr. Poliak. Dr. Poliak, thank you for preparing this presentation and for taking the time to share it with the Gleeble community. The floor is yours.
Hello, everyone, and good time of the day wherever you're staying. Dan, thank you very much for introduction. And I especially want to thank DSI for this opportunity to share some portions of our work we do to support our manufacturing operations. So our objective here, R&D Center supports basically this type of activities. We develop new product, we develop new steel manufacturing process, we improve and tune the existing processes because the world doesn't stay the same all the time, so we need to tune the process for the new product. We transfer products between various ArcelorMittal facilities within the United States and all over the world. Of course, because it's manufacturing, there are always some manufacturability issues arise, and part of our responsibility is to help the mills resolving these things. And also we are involved in application of our steel products at customer sites. Because of that variety of our tasks, we have a very wide variety of equipment here. And our Gleeble lab is just a part of the tools, of the research tools that we have here in the U.S. Research Center. The main objective is for us is to provide very quick response to the requests from the production facilities. That includes new product manufacture, new product development, because the faster you develop the product, the faster you commercialize it, the faster you get the payback. So because of this objective, because of this condition of meeting, we are not involved in developing very sophisticated simulations whatsoever, but we rather use simple simulations that we can perform quickly and deliver the results to the mills quickly in easy fashion that can be easily understood by the mill people, interpreted and implemented. the basic simulation, the main challenge that we face here is that lab conditions never ever reproduce industrial conditions. So part of the work is to translate the results of our simulations and our research into what I would say mill language, so that we could implement the results using some sort of extrapolation operations, extrapolation tools, and so forth. Our Gleeble lab, as I mentioned, is a part of our research tool parks. We have 3,500 machine with a torsion MCU, and quite recently we upgraded the control system to GDC, and it gave us a lot of new capabilities. What we're using this machine for is, of course, deformation resistance analysis of flow curves, constitutive analysis, strain hardening behavior, you name it. We use these results to help mills setting up their rolling practices, and that includes recrystallization studies, of course, and strain-induced transformations. High temperature torsion tests, we also run it basically for plate applications, hot ductility tests for casting applications. We also use quite extensively pyrometry, pyrometer calibration, simulations of surface oxidation. We support some of the welding operations in the mill, some because we also have welding simulators, which are much more powerful, and so we combine the Gleeble in those simulations, and we of course involved in most recent problem of liquid metal embrittlement. Let's start with how we support the casting simulation. When we cast slabs not always perfect. The liquid steel is cooled, and over cooling and handling and transporting the slabs, slabs crack. And here you can see the illustration of how they can be cracked. And then these slabs are basically not usable for further processing. So one of our tasks is to find out why the slabs crack. And to do that, excuse me, to do this, we perform the hot ductility measurements that imply heating this tensile specimens to a very high temperature, soaking and pulling to different temperatures, and pulling and tension. This scheme shows you how we machine the samples from this lab, and on top you can see the geometry of the sample. We use the round cylindrical specimens with the pressed cross section in the center, just because Gleeble mainly uses the direct resistant heating, so we have to make sure that the specimen fractures at the point where a thermocouple is welded. Although this is not a very comprehensive tension testing, we see it as an advantage, because when the slabs crack, that means that there are already some defects, stress concentrators present in the slab. So we are focusing on the localized deformation that gives us an idea why the slabs actually cracks, not why the crack is initiated. So to our opinion, this kind of heating in the Gleeble is advantageous compared to uniform heating with induction furnace or with a radiant furnace. Oh, I see what my problem is. My problem is that when I change the pointer mode, it doesn't work anymore. Typically, all steels exhibit what we call ductility trough in a certain temperature area. There are several types of ductility troughs when the slabs are cooled, and those troughs, those regions of very low ductility of cast steels, are related to different metallurgical phenomena, like precipitation, different kind of non-metallic inclusions and stuff like that. With our ductility measurements, we actually can detect some of ductility troughs using this reduction of area criterion. We can also measure the stress at fracture and its temperature dependence. What is interesting is over the years, we tested about 200 compositions from various slab sources, and we have built a database that allows us for this kind of regression. So when the steel making plant asks us for ductility data, we can do both things. We can test the samples directly, and we can derive the ductility from the regression equations that were built based on our multiple tests done before. Another thing where we use another aspect of our application to casting is typically if the caster is curved, the liquid steel goes down and is being bent and unbent as it crystallizes. This kind of deformation can also induce fracture of the slabs, cracking, and other very unpleasant things. So part of our task was to determine what is the safe curvature radius that this particular steel grade can sustain during crystallization. This is just an example for one of our steels. Of course, the susceptibility to fracture during crystallization depends on caster configuration, casting speed, and of course on chemistry. So when we provide this kind of data to the mills for the given chemistry, that helps them to adjust the casting speed, temperature distribution in the mold, and they find that very, very useful information because it can help them preventing slab cracking. There's another aspect that when the steel is being cast, the mold is continuously cooled, and the steel is continuously cooled by water spraying onto the surface. So the surface temperature basically changes as the steel travels through the caster. So the surface temperature oscillates like this, and this can facilitate cracking as well. The Gleeble machine, with its high flexibility and temperature control, allows us to simulate this kind of thermal cycling on the surface, and then we perform ductility tests, and we show that this thermal fatigue, very low cycle thermal fatigue, can contribute to ductility loss. So there's one more application, and it also just due to flexibility of Gleeble machines in terms of temperature control, temperature variation, and so forth. This is a very important result. We just obtained it recently, and our steel makers are very happy with this. this kind of simulation. However, our main application of Gleeble machine is hot rolling, assisting the hot mills in their operation. And here we have to look at the philosophy of our simulations. So when we have a steel, we have a material, and we have a tool to process this material. The tool does not depend on the material. So we have to adjust the hot mill, the tool operations to process the given material to get the desired mechanical properties. In other words, we have to find out what is the best way to process the given material through the given hot mill. If we want to have the same steel processed through another mill, that will be a totally different story because all the mills are different. They differ in their capabilities, they differ in the timing and pacing, cooling capabilities are different, boiling capabilities are different. So we run the Gleeble simulation to adjust different products to different hot strip mills. Oh, not only hot strip. So our Gleeble simulations are used to characterize material behavior, not tools, and then we use this information to add up the given hot rolling mill. A little short description of what's going on in rolling. The major parameter in rolling is the rolling force, which is contributed by three major factors. First of all, that's deformational resistance of the material. Then that two parameters of the rolling mill, contact lengths, geometrical shape coefficients. So with Gleeble, we addressing only the deformation resistance of material. We cannot do anything about the other two contributing factors. So Gleeble, as you well know, helps us to determine material properties during deformation. Deformation resistance, this is it. And what happens in rolling, usually deformation resistance is determined in terms of flow stresses and is described using the so-called flow curve or straight strain curve. However, in rolling, the work roll sees simultaneous deformation changing in the roll line from 0 to whatever the past deformation is applied. So rolling models operate with what they call mean flow stress, and that is what Gleeble helps us to determine. As the instantaneous flow stress is the mean flow stress as the function of strain rate, and temperature. During hot deformation, the instantaneous stress basically attains a steady state value, which with increasing strains becomes strain independent. We found that the mean flow stress at high strains converges with the instantaneous flow stress. That's very convenient property of mean flow stress, so that we could use instantaneous stress values to approximate mean flow stress. We don't need numerical integration of the flow curves all the time. And then we can translate it into deformation KFM values that MEO models are using for their operations. So with this introduction, let me also briefly give you an idea of hot strip rolling, how it is done. The slab is reheated in the reheat furnaces here, and then it is rolled in roughing mill, basically used to reduce the thickness of the slab substantially. Then there is a delay table, and the bar goes into the finishing mill. The main feature of the finishing hot strip mill is that the bar is simultaneously in all of the rolling stands. So it is continued tandem rolling mill, and the bar progressively reduces its thickness as it travels through this mill. After exiting the mill, the strip is cooled with this controlled cooling on the runout table, and the coil is produced by the coilers at the end of the mill. Important parameters for the mill is to set up the rolling speed. Here, very important feature is what we call mass flow constants. The mass traveling through the mill is constant, so the thickness, because the width is kept constant in this kind of rolling, the entry thickness to exit thickness ratio is exactly the ratio of the speed the strip exits from the mill to the speed the strip enters the mill. Now, I mentioned the delay table in front of the finishing mill, and so that is why the temperature is not always constant. It typically decreases as the bar or strip is being rolled, because the tail of the strip here sits on the delay table for a longer time than the head. So it loses the temperature because this speed is much slower than the exit speed. For this reason, to compensate for these temperature losses, the mills apply acceleration. So after they threaded the strip through all stands, they start to accelerate the bar, speed up the rolling to somehow compensate temperature losses of the tail and entering the mill. But that's not always successful, and the temperature may decrease from the head towards the tail as it exits the mill. Now, I apologize for the scales here. They're in Fahrenheit degrees, but that's the actual mill data. The speeds are also in feet per minute, so don't be confused with these numbers. Of course, when the speed of the bar going through the mill changes this way, it does change the strain rate at which the steel is deformed. And here are some examples of how the strain rate changes depending on, of course, of the thickness of the entry thickness and the final thickness of the strip. This example gives you an idea. It's basically an order of magnitude increase in strain rate. And you can see how the strain rate can change depending on the final thickness of the bar. Just giving you an idea of the orders of magnitude that the mill sees in terms of strain rate. Important is that the Gleeble operations, Gleeble machine cannot reliably reproduce very high strain rates, just because the time of deformation is very short. So we need to accelerate RAM and decelerate RAM in compression, for example. In torsion, it is easier to obtain this kind of strain rates, but the strain rate is not uniform if we're using the round bar sample. So this is a challenge for not only for Gleeble machines, but for other machines to simulate more or less accurately the strain rates of about 100. and to make sure that the strain rate is uniform throughout the test. That is why we need some sort of translation algorithm to translate the results obtained at lower strain rates to what we can see in the mill. This is, of course, you guys all know this, that at high temperature, the flow curves look pretty much like this. They have the steady state, as I mentioned before. The shape of the flow curve tells us something about what kind of microstructure is developing during deformation. There is common agreement that if this flow curve exhibits the stress peak like this before steady state, this is typically associated with dynamic recrystallization. On the other hand, the absence of the stress peak is typically indicative of the absence of dynamic recrystallization. There are also some flow curves of, I would say, intermediate kind of shape. They're very subtle peak, barely visible, but the stress is declining. So John Jonas called it limited dynamic recrystallization. I tend to agree with his definition. And when the temperature goes up, there is definitely change in the shape of the curve from no dynamic recrystallization to the direct kind of shape. The same thing happens when the strain rate is decreasing. And we all know that these two parameters are combined in what is called Zinner-Hallemann parameter, or temperature compensated strain rate. It is a more accurate definition. The number that actually normalizes these two processing parameters, strain rate and temperature, is called apparent activation energy. So when we want to describe the temperature and strain rate dependence of stress, whether it's steady state or instantaneous stress, we need to find what's the value of their activation energy for deformation. In our way of translating the test results into mill language, we often, most of the time, we use steady state stresses. These values of stresses, because they can give us an idea of what is going on with microstructure. It's a better idea than if we use strain dependence or dependence on the initial microstructure. Then we can go deep. Once we establish the dependencies for steady state stresses, we can go deeper and analyze what's happening in the small strains or how the initial microstructure affects this. We came up with a very simple determination of activation energy using just simple mathematics, simple property of partial derivatives. And those partial derivatives are called strain rate sensitivity for temperature sensitivity. I call it engineering sensitivities because they're not exactly partial derivatives, they're just the differences. And what is important, so how we do this, we select several stress levels and then follow the print definition. We plot the strain rates and against the inverse temperature for given stress levels, and the slope gives us this activation energy, which by this definition is just the ratio of temperature sensitivity to strain rate sensitivity to stress. We don't bother putting any physical explanation for this activation energy. We think it doesn't have any meaning. It's just a parameter. So we calculate it from our test data and then give this information to the mill. They use it very quickly. Based on this, we developed what we call the four-point test procedure that allows us to predict flow stresses and hence deformation resistance, mean flow stresses, in the mill. The first step was to make sure that the Gleeble data and the numbers that we obtained during the test are translatable into mill language. The mill wants not the stresses per each stand. They want the ratio of the deformation resistance in the last stand to the first stand. That is linear. This linear relationship allows them to set up the level 2 model and then adjust it for the rolling. So we ran the trial test, low carbon aluminum kiln steel, and we found out, well, we're pretty close. This ratio that we obtained in Gleeble by extrapolation is pretty close with what mill model calculates during rolling. So based on this, we were very confident that we could provide the information using this just simple things, simple 4-point test. With the sensitivities, we can actually modify temperatures and strain rates and adjust the numbers for any entry-exit combination of temperatures and speed. This procedure is also being used to set up new grade, set up the strip rolling of new grade. Again, using the sensitivity parameter and obtain the stress ratio. So it means we give the mill information, numerical information, quantitative information of how harder or how easier the new grade to roll compared to the grades that they are already producing. Now, the mill operates in the following way. When the new grade comes in, the hot strip mill runs several, like 10 or 15 dummy slabs to teach the rolling model. So the rolling model needs to be learned, and they roll 10 to 15 slabs to obtain the learning of the rolling model. Those dummy slabs and strips then scrapped. So this is a very costly stage of production. With this data, with our data, when we give them an idea of how easier or how harder the new grade is compared to the existing grade, the number of the dummy slabs can be reduced substantially, from 10 to 15 down to 2 to 3. Then the model learned, and they run the production slabs. So this is a very important and efficient tool of cost saving when the new product is introduced to production. And of course, I forgot to mention that we tested about 100 steel compositions in the recent 15 years, and we also built a database and regression type of dependencies based on this database, so that we could calculate deformation resistance. That saves even more time and even more money for when the new grades are coming in. The same simple procedure of compression allows us to define what are the limits in terms of dimension of the bars that the mill is rolling. The limitation of the mill is the roll force. So we can calculate how thin and how wide the strip could be rolled on this particular hot rolling mill with this particular limitation. So we can actually build a table of thickness and width capability for any kind of product that can be rolled on this mill. And it's a very simple equation. Only we can determine and Gleeble test the deformation resistance. We take these parameters out of the tool. We know the limiting force. So the width is inversely proportional to the thickness, and that's how we calculate the limits and the dimensions of the steel product. Another important application is recrystallization control. When we hot roll the material, the material is recrystallizing because of high temperatures. The goal of any hot rolling is to avoid partial recrystallization in the final product because partial recrystallization cannot be reliably controlled. Very slight variation, say in temperature of the bar, can change the volume fraction recrystallized, so we can obtain very non-uniform microstructure in between the passes, during the rolling pass, after the exiting the mill. So the transformation of microstructure will also be affected. And here is the diagram of the actual temperature distribution along the strip exiting the mill. You can see that the temperature variation is 60 degrees Celsius as the bar goes through the mill. So this is quite sufficient to induce very large variation in the fraction of partial recrystallization. So the goal is to avoid partial recrystallization by any means, and that applies to dynamic recrystallization and to static recrystallization. Dynamic recrystallization control can be done if we consider that steels are power law materials. When we plot steady state stress against the Zinner-Hallemann parameter, we found different microstructure depending on Z, and we introduced two, or basically four, limiting parameters, either temperature or strain rate, that is presents the boundary between full and partial dynamic recrystallization, and same as a boundary between partial and zero dynamic recrystallization. Or we can introduce the respective Z parameters. So the convenience is that we know the strain rate or rolling speed and temperature, and we could use either of them to set up the no recrystallization or full recrystallization rolling schedule. Based on our experience, I can tell you that the majority of steels we're dealing with exhibit this kind of behavior. It's something very confusing, but this type of behavior was actually reported a long time ago, 50 years ago. Interestingly enough, that say strain rate sensitivity of stress or temperature sensitivity of stress is changing non-monotonously. For dynamic recrystallization range, it does not depend on temperature or strain rate, and pretty much constant. Same with when dynamic recrystallization is absent. So when we determine the strain rate sensitivity from our Gleeble test, we can easily translate it into mill data saying, look, guys, you have to enter this value or this value into your model, and then you will be okay in terms of avoiding recrystallization or facilitating. For curiosity purposes, we can calculate the volume fraction of partial recrystallization using the conventional lever rule or mixture rule for sensitivity. That feature of dynamic recrystallization allowed us to build some sort of phase diagram, I would say. It's not the phases in our conventional understanding, it's the diagram that shows the boundaries between different processes. And say, if you select the strain rate or rolling speed, you can determine the temperatures at which dynamic recrystallization either stops or goes into full completion. We build this kind of diagrams for different kind of steels and actually use this as an example how we set up the plate rolling finishing schedule to produce no recrystallized, no dynamically recrystallized steel. See, we designed the first 4 finishing passes so as to provide as much dynamic recrystallization as possible. But then temperature went down, so we proposed to have the bar on hold and drop the temperature substantially and finalize the dimension, in the no dynamic recrystallization range. It actually helped us to improve properties of line pipe X70 grade substantial. This is again this 4-point very simple method. Like I said, we have to supply the mills with the sensitivity data. We do that for different kind of grades, and they're very, very happy with this data in terms of setting up their another recrystallization control is related to partial to static recrystallization, and this is much more challenging because, first of all, static recrystallization does not produce immediate mechanical response, so we cannot directly use mechanical tests to assess static recrystallization. And there's one, and time after deformation is one additional parameter that affects all the kinetics and the onset of static recrystallization. So we derived 2 equivalent critical conditions for static recrystallization in the interfaces. One is when incubation period for recrystallization is exactly equal to the interpass time, whether it's hot strip rolling or plate rolling, or and when the recrystallization stop temperature is equal to the temperature of the bar in the interpasses. This is a very simple definition, but we are building. We have not finished it yet. We are building a sort of a model that allows us to predict whether or not the static recrystallization occurs during rolling out. As I mentioned, I'm running out of time already. This slide is giving you an idea of what kind of interpass times we see during hot strip rolling, and they are pretty short, but in the first passes, we still can see that it is possible, depending on the chemistry, that static recrystallization can take place. Important is that the interpass time is shortened as the bar goes through the finishing mill and hot strip rolling process. Combining these two kind of recrystallization control method, we can actually tell the mill whether or not recrystallization is taking place. We determine the recrystallization stop temperatures for several grades. They are listed here, and unfortunately for us, these temperatures are below the finishing mill entry temperatures. So that tells us that many of advanced high-strength steels do undergo dynamic recrystallization in the first passes of the hot strip mill, of hot strip rolling. Static recrystallization is also possible, as I mentioned before, because the interpass times are long enough for this recrystallization to happen. Like I mentioned before, we are developing the model. Typically, what people are doing, they use double or multi-heat testing with different interpass times or stress relaxation method to determine whether or not static recrystallization occurs in between the deformation operations. We're developing the model based on similarities between dynamic and static recrystallization. And this model allows us to estimate whether the recrystallization stop temperature is below or above the temperature of the bar. And we provide the mill with the results that guide them as to how to control recrystallization by changing the finishing temperature or by applying interstand cooling so that the recrystallization will be avoided. These are two actual temperature profile at the exit of the hot strip mill. And you can see that lowering the finishing temperature can help avoiding recrystallization before transformation starts. So this is kind of information we're still working on, but we're giving the mills at least the estimate for thermomechanical processing for no recrystallization thermomechanical process. Plate rolling, we also use the torsion tests to simulate the plate rolling. Plate rolling feature is, it is reversible. So the bar goes in the front direction, forward direction, and then in a reverse backward direction during rolling in one stamp. The strain rates are low, temperatures are much wider, but the problem is, one of the problems is the plates are thicker than hot rolled strips. So we have substantial true thickness gradients of temperature, stress, microstructure, and we need multiple Gleeble simulations to set up the roller with a single plate. We are working on the way how to reduce the number of simulations for plate rolling. And same applies to interpass recrystallization, because in plate rolling and reversible rolling, interpass time increases from pass to pass because the length of the strip of the plate increases as it's being rolled. And we are talking of much longer interpass times compared to those in the hot strip rolling. So for plate rolling, the static recrystallization control becomes very important. Again, we are trying to use our model. It's still under development. We have positive results, promising results from the plate mills as to prevent the static recrystallization between the passes. Unfortunately, only criterion here is measuring the final progress of the plate and looking at microstructure after transformation. One more thing that I would like to talk about this here is, and it especially concerns with the plate rolling as abnormal behavior of some characteristic strains that we see during the compression absorption test. Typically, the peak strain or critical strain for dynamic recrystallization increases as the temperature goes down. However, at some point, we see it starts to decreasing as the temperature is decreased. This is known phenomenon. It's attributed to dynamic strain-induced transformation. And we actually did this. We took the graph of the fixed strain, rotated it by 90 degrees, and we obtained this kind of curves, which resemble the CCT, the TTT, I'm sorry, curves of conventional phase transformation. So using this kind of graphs, we can separate dynamic recrystallization from the phase transformation. We can determine the temperature at which transition is happening, transition and controlling mechanisms. And we can derive, similar to dynamic recrystallization, we can derive the transformation on set temperature at given strain rate, or the transformation on set strain rate at given temperature. So we can provide the mill with information when, if the transformation is going to happen during rolling. What is the transition range? What kind of temperatures they should be careful about, and so forth. This slide just illustrates how the strain rate affects the transformation, or how different grades can be transformed during deformation. Why it is important? The transformation of austenitic ferrite changes the volume of steel. And so it changes the mass flow. So when the steel is transforming in the mill, the mass flow is no longer constant. If the mill knows this, it can be taken care of. But if the mill does not know this, the temperatures are not properly set up, the strip will cobble in between the stands because mass flow is not constant. So this is a very important information that we supply to the mill to make sure that the rolling is stable, to set up the tension, interstand tension for hot strip mill, and avoid cobbles, because cobbles are very costly to fix. We also use our Gleeble machine to assist the mills in setting up the tension on the runout table between the last stand and the coiler. There are two types of tension here. We do run tensile and compression simulations to determine the yield strengths in plane strain, tension, or compression. For tension, the information is fed into the tension into the coiler control system. For compression, it is necessary to know how to bend the strip around the manual and not to break it. One more application which we are very fond of is using the pyrometers. Pyrometers are being used all over the place, but mostly our concern is with the annealing and coating line. We measure the temperature of the samples in the Gleeble by thermocouple and by pyrometer. And when those temperatures are not match each other, that allows us to calibrate the pyrometer and to measure the emissivity of the strip. Specifically, we can, in the chamber, we can achieve different kind of atmospheres and different extents of surface oxidation. We can closely simulate how the strip oxidizes in the annealing and cooling line, how its emissivity changes during heating and cooling, and what the pyrometers see in the mill, how they measure temperature, and how it compares to the actual temperature of the strip. This is data fed directly into the annealing and coating line control system. We aim the pyrometer on one side, we weld the thermocouple on the other side of the strip, calculate the delta temperature, calculate emissivity, and we can calibrate the pyrometer. This is, of course, not certifiable calibration, but the mills bring the pyrometers here to check whether they're good or not, whether they need to be replaced or not, and so forth. In plate manufacturing, one of the most important tests is the ductility, the toughness of the weld joints. So our Gleeble machine, of course, has the capability to simulate different welding cycles, and that's what we're using. We came up with this simple idea to use full-size Sharpie sample, heat treated for a given thermal cycle of welding, and then the machine the notch and test it for Sharpie toughness exactly at the point where thermocouple is welded. I think that this kind of tests use the advantage again of the gradient heating of the sample in the Gleeble because we're testing the toughness at exactly the weld point. We're not seeing any effect of the rest of the material on the weld toughness. So this is, I think that's a very important advantage of the heating, of the resistant heating in Gleeble. Basically, this type of heating is very advantageous because we can change the geometry, the width of the sample, the diameter of the sample, and we can control the temperature distribution along the sample. We can control gradient, we can control the cooling and heating rates, and that allows us to save time and material, especially for analyzing this kind of phenomena, recrystallization, cold sheets, phase transformation, surface oxidation, temperature martensite, tempering of martensite. And I would like to emphasize that the effectiveness of such variable temperature simulation is much enhanced by the Gleeble GDC system. It gives us a lot of flexibility, and we're very happy that we have upgraded to GDC recently. This is an example how we use that flexibility to study tempering of martensite. So we loaded a sample with variable widths into Gleeble. We measured simultaneously temperatures and then hardness at those locations. So you can see how the martensite was tempering, what kind of microstructure. Just using a couple of samples, not many samples. So machining costs money, costs time. Testing costs money, costs time. This allows us to save a lot of time, money, and labor in performing our test. Another application is, again, using the advantage of direct heating and thermal gradients is studying dynamic strain-induced transformation during hot tension. Fortunately, I already ran out of time. This is a very interesting kind of application that we recently discovered, but it helps us to predict whether in this hot rolled strip, dynamic transformation takes place, how it can affect edge cracking of hot roll strip, or how it can induce the residual stresses that contribute to the defects of the sheet material after hot rolling. So the conclusion is very simple. Gleeble machines are very versatile and capable to render excellent possibilities of designing numerous kinds of simulations. Over the years, what we used, our Gleeble machine is proving as an essential tool to support multiple steel manufacturing, and which results were very much appreciated by our ArcelorMittal facilities, and it continues to raise our reputation as a research. I see Gleeble as a political tool to establish good relationship with research and production facilities. So Gleeble helps us a lot to go from this kind of situation to this kind of situation. With this, I thank you very much, all of you, for your attention. Down here is my email. So should you have any questions, I will be very happy to answer them and to provide more details of what I was talking about. Thank you very much.
Thank you, Dr. Poliak. This was a great presentation. I really appreciate you taking the time to make the presentation, create it, and then spend some time with us this morning sharing. I'm already getting messages from people around the world telling me how much they appreciate it. So thank you. We are kind of running out of time here. I do want to thank Dr. Fulvio Siciliano and Eric Dietz on our team. They have been answering some questions privately in the chat. So appreciate their help in answering some of those great questions. We don't have time for a live Q&A, but again, Dr. Poliak's email address is down at the bottom there. If you missed that, you can also email me, and I can share that with you. If you do have questions, any technical questions about the operation of your Gleeble, please contact our service team. Currently, most of them are not traveling a whole lot given the pandemic. However, the best way to get hold of service is always the service portal, and that is available to current customers. You can go on to our website, Gleeble.com, click on the resources link at the top area, and then go down to the service customer support portal. There's a knowledge base, an FAQ. You can also create tickets to get support. So that is the best way to get support. I hope you do take advantage of that. If you have any questions about how the Gleeble can support your research, please email me or any member of our team, and we'll be happy to connect you with an application expert that focuses on the research that you're doing or in the region to help you locally. So again, I want to thank Dr. Poliak for a great presentation. We really do appreciate it. And thank you for joining us. Please stay safe and healthy. Have a great day.
You too.